So let's continue with the topic rational power spectra. Okay, so we know that this xn sequence is a stationary random process. Okay, and the power spectral density of that we have taken gamma x, or we just take the z transform of the autocorrelation function. So we know that with the previous analysis, gamma xxz is equal to sigma w square hz and h into hz inverse. So we can just assume that this is having a having a rational. This is a rational function, means it is having a polynomial in the denominator as well as in the numerator. So we can just write it down. Gamma xx z is equal to sigma w square bz divided by az. Okay? It means it has a z polynomial in the numerator as well as denominator, multiplied with h z inverse, that is b z inverse divided by az inverse. Okay, is that fine? And here we can just put the constraint on the z, that annular region. So it is from r1 to r2. Okay, now uh, basically this whole thing is a rational power spectra. Let me just write down with different color. So this is your rational power spectra of xn. Okay, and the roots of these polynomials, that is bz and az, lies inside a unit circle. Okay, so let me just write down this part also. The roots of bz and az, roots of these polynomials, that is, what are the polynomial? Az, that's a denominator polynomial, and bz. Okay, so that lies inside a unit circle. Okay, so obviously it says that this indicates that it's a causal and causal, stable, and minimum phase linear system. When we are putting these constraints, it's a causal, stable, and minimum phase linear system. Okay, so if that's the case, let me just change the slide first. So this your hz is equal to bz divided by az, and I told you that the roots of these polynomials are lying inside a unit circle. Let me just expand these polynomials. Summation bk z power minus k, and where k is from 0 to q. The denominator polynomial is 1 plus summation ak z power minus k, and k is from 1 to, let's say this is small p. Okay. Now note one point over here, that is we ha we have written here the limits are from k is equal to 1 to p, but this part you can say, if you put the limits, or you can say, let me just write it completely for better understanding. bk z power minus k, and k is equal to from 0 to q. In the denominator also we can just put the same limit ak z power minus k, and again the k is from 0 to p, whereas a0 is equal to 1. Okay, if a is equal to 0, a0 is equal to 1, then you can write in this way also. Anyway, so uh, when we are talking about this z h z only, here one more constraint you should put, that is mod of z is greater than r1. Okay, mod of z is greater than r1. So this hz, this is causal, stable, all the poles are inside unit circle, and minimum phase linear system. Okay, therefore the random process xn uniquely represent the statistical properties of the innovation process Wn. Okay, since it's the causal, stable, and minimum phase linear system, so the random process xn uniquely represents the statistical properties of the innovation process Wn and vice versa. Uniquely represents the statistical properties of the innovation process Wn and vice versa. Okay, so that's one thing. Now let me change the slide first. Let me just write it again. Hz is equal to bz divided by az summation bk z power minus k, where k is from 0 to q, whole divided by 1 plus summation k is from 1 to p ak z power minus k. So let me now for this linear system. Okay, for this linear system with a rational system function. So this is a rational system function having a denominator as well as numerator polynomial, or it has zeros as well as poles. So the output xn. Now remember, in the previous lecture I just told you about the generation of the process xn from a noise. I told you about this thing, something hz, where the input is wn, a white noise, and the output is xn. Okay, so let me just write it in this way. Now basically, uh, if you use this system function hz is this, in that case you can say okay, x z divided by wz is equal to summation bk z power minus k divided by 1 plus summation ak z power minus k, and just after taking the inverse z transform, so you will be getting sequence something like this. You'll be getting xn plus summation ak x of n minus k, where k is from 1 to p, that is equal to summation bk w of n minus k, where k is from 0 to q. So that is xn can be written as xn is equal to minus summation ak x of n minus k, and k is from 1 to p, summation bk w of n minus k, and k is from 0 to q. Okay. Okay, is that fine? Okay. So now from here there are three specific cases we can see. One is called auto regressive process, moving average process, and auto regressive moving average process. So we'll see. Let me just write this on the next slide. We have seen that we have a system function xz, and the input is wn, and the output is xn. Okay. So and also you have seen that xn is equal to minus summation ak x of n minus k, where k is from 1 to p, the summation bkwn minus k, that is from k is equal to 0 to q. Okay. Now based on this we can have three specific cases. Case 1, case 2, case 3. Let me solve that. Three specific cases. First case is, suppose that b naught is equal to 1 and bk is equal to 0 for k is greater than 0. What does it mean? Basically, the what it indicates basically that this implies that the numerator polynomial bz, that is equal to 1 of the rational spectra, of the rational power spectra, the bz is equal to 1 when b naught is 1 and bk is equal to 0 for k is greater than 0. Okay. So it means that this implies that we have hz is equal to bz upon az, and bz is 1 divided by az. Okay. And what is this system now? Now this system is an all pole system. We call it all pole system. Okay. So we call it, this system is nothing. This is a all pole system of filter. Okay. If that is the case, so this also implies that xn summation ak x of n minus k, and k is from 1 to p, this is equal to wn. Okay. Is that okay? Now from here what we can say, that this specific case is a all pole system, and we call it auto regression, that's AR process. autoregression process. The other thing from here is the noise whitening filter for generating the innovation process, that is WN, will be an all zero filter. Because what was that filter? If we are taking uh, the inverse of that system, so that of Hz, it will be 1 upon Hz, and since Hz is a all zero filter, all pole filter, so 1 upon Hz will become a all zero filter, and when it's a all zero filter, so the noise whitening filter for generating the innovation process will be an all zero filter. So let me just write it here. H z of 1 upon h z. So here the input is now xn and the output is wn. Now this filter will be all zero filter. Okay. I repeat, the noise whitening filter, for the noise whitening filter, this is a noise whitening filter for generating the innovation process. It's generating an innovation process wn is an all zero filter. So we have seen the first case, that was the autoregressive process, and now we'll be moving to the next specific case. We call the next case is moving average, that's MA process. Okay. Third case we'll take on the next slide. Now for this case, for the moving average process, you take AK is equal to 0 for K is greater than equal to 1. For K is greater than equal to 1. So if that is the case, so you will find that this implies that the denominator polynomial of hz, that is az, will be equal to 1. If this is equal to 1, it implies that hz will be equal to bz only. And when this is the case, now this system function is nothing, it is a all zero filter. Okay, it's the all zero filter. So if you apply this, so that implies the xn sequence will be equal to summation bk w of n minus k. Okay, and the k is from 0 to q. Okay, so we'll be getting this. Basically, you are generating this xn from a noise only. Okay. Now, I was also talking about the noise whitening filter. The noise whitening filter is nothing that is 1 by hz. Okay, where the input is xn and the output is wn. In that case, basically, this noise whitening filter for a moving average process. Okay, this will become a all pole filter. Okay, do not confuse with the third case. This is I'm just discussing the second case only. Okay. So this noise whitening filter for the MA process or moving average process will be a all pole filter. Okay. Now let's move to the next slide to discuss the third case. Okay, second case was MA process. Now come to the third case, that is, we call it auto regressive moving average, that is ARMA process. Okay. So in this case, you know that hz is nothing is equal to bz divided by az. Okay. So this is having both poles and 0. So it is having a both component, that's a moving average part. This is a moving average part as well as autoaggressive part. Okay. So that's why we call it autoaggressive moving average process or ARMA process. Now, if you just talk about the noise whitening filter, basically, the noise whitening filter, it is 1 upon Hz, that's the noise whitening filter. The output is noise on Wn, the input is Xn. Okay, that's a so. So the inverse for generating the inverse for generating the innovation process, that is Wn from the Xn, will also be a pole zero system. It also contains poles and zero. You can say that 1 upon Hz is equal to Az upon Ez. Means the poles will become zero and zeros will become poles. Okay. So we have seen the three different cases from the above equation. The first one was the AR process or auto interaction process. The second one is the moving average process. In the moving average process, there is no denominator polynomial, or it's one only. And the last one which we have seen, it's the ARMA process, where we have both poles as well as zeros. Now, on the next slide, I will be discussing the relationship between the filter parameters and autocorrelation.